An airplane is flying with an airspeed of 475 miles per hour on a heading of 070 degrees. If an 80 mile per hour wind is blowing from a true heading of 120, determine the velocity and direction of the plane relative to the ground. So first, let's sketch a picture of this. You have a plane, so this would be north and this would be south, and you have a plane heading 475 miles, that's the scalar, per hour, at a bearing or a heading of 070. And this is the notation for whenever you're dealing with an angle from the north going in the clockwise direction. So we know this is a 70-degree angle. If an 80 mile per hour wind is blowing from a true heading of 120, true heading also, meaning from the north, but this is blowing into the plane at 80 miles per hour. So what is this saying? This is saying that you have an airplane and you're driving it exactly this direction. Now, if this were a car and you were on the road and you headed it in exactly this direction, it would go exactly that direction. But airplanes are different. They're not tied to the ground. And so if a wind comes along, the plane is going to believe it's doing this, but the wind is going to push it out of that alignment. And in fact, since it's a vector, I can take this 80 mile an hour vector and I can move it end to end with the plane vector, with the vector that tells how the plane is moving. And this is a legal move as long as I keep my magnitude and my direction exactly the same. So the direction by angle and the direction by which way it's pointing. So what would the final effect be? And I'm going to draw it over here so I don't muddy up my workspace. I have my plane, and I know that my angle is 70 degrees there, and I know that I've got a wind blowing against it in this direction, not putting a bunch of stuff in here until I need to label it. What's the final effect? Well, the final effect is the resultant vector that I've sketched here in blue. So the plane thinks it's going this exact on this trajectory, 475 miles per hour at 70 degrees from north. The wind comes along at 80 miles per hour, 120 degrees from the north, and the effect of the plane is that it's going to fly over houses right here, even though it thinks it's going to fly over houses right here. Not that a plane can think, but that's what we're looking for, is what is the magnitude and the heading of this blue angle or this blue vector. So let's move some labels over. I know that this is an 80-degree magnitude. I know this is 475. And I know that, well, this is 120. So I know what this angle is here. Let me change the color. So I know that this angle is 120 minus 70, which is 50 degrees. And then using opposite interior angles of a transversal across parallel lines, I can say that this is also 50 degrees. Clearly, I haven't sketched this to proportion. Doesn't matter, I just need a working model to look at. So where am I? I want to know the magnitude of this blue vector. And luckily, I know the other two side lengths or magnitudes, and I know the opposite angle, which means I can use law of cosines, right? So the magnitude of vector, let's call it C. The magnitude of vector C is going to be equal to whatever the length of C is. And from the law of cosines, I have that's the other two squared and added minus 2 times the other two sides times the cosine of the opposite angle. So if I plug all my values in, I get 475 squared plus 80 squared minus 2 times 475 times 80 times the cosine of 50. If I put all that in my calculator, I get the value c squared equals 1,000, no, that's wrong, 183,000 173. If I take the square root of both sides, I get that the magnitude of the blue vector, or c, is 428 miles per hour. Okay, so I'm halfway there because I'm asked to determine the velocity, which is the magnitude, and I want the direction of the plane relative to the ground. So I need to find out what c is. So for this one, I can use the law of sines and find alpha. Once I have alpha, it's easy for me to find theta. Let's call this theta. So first, let's find alpha. Well, I have the sine of alpha over, well, what's the opposite? 80 is going to be equal to the sine of 50 over whatever the opposite is, and that's what I have here, 428. So the sine of alpha is equal to 80 times the sine of 50 over 428. That equals 0.143. Now I'm going to take the arc sine of 0.143, and that tells me that alpha equals 8.23. So theta, therefore, is equal to 70, this entire distance, minus alpha, 8.23, which is equal to, or approximately equal to, I guess I should say, 61.77, so 61.8 degrees. Therefore, I can say that relative to the ground, the plane is flying 428 miles per hour at a bearing or a heading of 0.62 degrees.